Hi again, Professor Bob Young, and in this video we're going to look at compound interest, the formulas your bankers love to use with you, and the number E and what is called continuous compounding. So compound interest, it says the formula for compound interest, which is interest paid on both principal and interest, is an important application of our exponential functions that we've begun. Recall the formula for simple interest. If you remember in a lot of your math courses before this, I equals PRT, P times R times T, where P is the principal, the amount deposited, R is the annual rate of interest, of course expressed as a decimal. They'll change it from percentage to decimal. And T is the time in years that the principal earns interest. Now suppose that the time is a 1-year time. Then at the end of the year, the amount has grown to A equals principal plus interest. Now let's show you where that next thing's coming from here. So let's go ahead up here and say when T is 1, we're going to get I equals PR. See, so this I here becomes PR. So the amount after 1 year would be P plus PR. Now, of course, if you factor a P out, you get what's in blue here, P times 1 plus R. So I hope that makes sense. The original principal plus interest. Now, if this balance earns interest at the same interest rate for another year, the balance at the end of that year will be, well, here's our first year, P plus 1 plus R, plus another P plus 1 plus R here with that rate. And notice again, if we factor, we'll get P times 1 plus R quantity squared. And after the third year, look what happens. We can keep doing this till we get P times 1 plus R cubed. So continuing in this way produces a formula for interest compounded annually. The amount down here on the bottom equals P times 1 plus R raised to the T power. So here is where they get the formula for compound interest. If P dollars are deposited in an account paying an annual interest rate, R, compounded N times per year, then T years the account will contain A dollars. Now I know this formula looks kind of scary, all going, oh my gosh, look at what this thing's become. Now I would give you this on the test. It's not really having the formula, it's knowing how to use it and input things in your calculator. So this is the formula for compound interest, compounded N times per year. Now we need to talk about some terminology here. Here's the banker's terminology for compounding N times a year. Of course, annually, we looked at N equals 1 time a year. Now they might compound things, banks do semi-annually. That would be 2 times a year. Quarterly, you've heard that on some of the news reports and stuff, the quarterly report, 4 times a year it would be compounded. Monthly, 12 times. Daily, 365 times. So there's all kind of fun things we can do with this. So let's look at example 1 here. Suppose we've got $1,000 deposited in an account paying 4% interest compounded quarterly. So notice we put 4 times in there, N would be 4. Find the amount after 10 years with no withdrawals. So writing the formula here, we're going to go ahead and plug in 1,000 for the principal. Okay. Notice N appears in the formula not once but twice, and since it's quarterly, we're going to go ahead and put that in here once but twice. The rate is 4% here, so they change 4% to a decimal, and this is for 10 years. Now, let me warn you, when you put this in your calculator, be careful, all right? I mean, I would try to put the whole thing in one shot. Now, notice here that they kind of do what's in the parentheses first, which sometimes works and sometimes doesn't. Now, since they had a nice number here, like 0.04 divided by 4, it worked. Now, I'm going to go back. I would go 1,000, parentheses on your calculator, 1 plus, put a parentheses there, 0.04 divided by 4, close parentheses again, caret raised to, and then put parentheses 4, and then you can put times in there, 10 power, close parentheses. All right, so here's the keystrokes. We're going to put 1,000. So here's how to do the formula every time, no matter what numbers they give you. Parentheses, 1 plus parentheses, 0.04 divided by 4, close, close. See, so for every open parentheses on your calculator, you need a closed one. Caret, parentheses, 4 times 10 power. So yeah, you've got more than one thing in the power there, so be very careful. So that is how I would enter it. All right, and if you do it right, you should get $1,488.86, rounded to the nearest cent now. Remember, these are dollars and cents here, so make sure that you round to the nearest cent when you do these compound interest formulas, and you will have one of those on the test. All right, now it says suppose $1,000 is deposited in an account paying 4% interest per year, compounded quarterly. How much interest is earned over the 10-year period? Now remember, we ended up with $1,488.86, but we have to subtract that initial 1,000, so we really made an interest $488.86, which isn't too bad. It doesn't sound like. All right. Example 2 here, finding a present value. Becky Anderson must pay a lump sum of $6,000 in 5 years. What amount deposited today at 3.1% compounded annually will grow to $6,000 in 5 years? Now notice here, that's the amount we're going to end up with is $6,000, and we want to figure out what amount to put in there to do that with 3.1% interest over 5 years. So notice again, since the N is 1 here, since it says annually, this is kind of nice because we end up with 1 and 1 here for N. All right, so this one's kind of nice because as we continue, we can say that 6,000 equals P times 1.031 to the 5th power. All right, now how are we going to do that? We're going to need our calculator here. To get P by itself, we would have to divide both sides by 1.031 raised to the 5th power. So you and your calculator must become 1 in this section. Okay, so here's how to enter this creature in red over here. All right, so be very careful when you enter this stuff. So I would go 6,000 divided by, and then I would put parentheses just like it looks, 1.031. And you know, I might even put a second parentheses in here. Let's try this again. Let's go parentheses, 1.031 raised to the 5th power, close, close. All right, because if you don't enter things right, you know, and you really have to practice, and you're going to make some calculator errors here. So the answer would be about $5,150.60 would have to be how much you put in order for this to happen. So, you know, maybe try doing it with only one parentheses and see if it makes a difference or not. Now, maybe in this case it wouldn't have, but I like to let my calculator know, hey, here is what I'm dividing, this 6,000, by, and I'll let it know all of that is being divided by 6,000. So be very careful entering things in this section. All right, now if only 5,000 is available to deposit now, what annual interest rate is necessary for the money to increase to $6,000 in 5 years? Well, in this case, we would just put the 6,000 in for the amount. We would know that the P is 5,000. So now what are they asking? They're asking what rate we would have to get here. So to get R by itself in this equation, so they're going to like put different things in for different spots. We are going to divide both sides by 5,000 first. Okay? And then we'll reduce 6,000 over 5,000 to 6/5. Now, notice here that they raised both sides to the 1/5 power. Now, you could have also, remember that 1/5 power is another way to write the 5th root. You could take the 5th root of 6/5 on your calculator and set that equal. So the 5th root will take out the 5th power here, leaving you with the 1 plus R. So here's another thing on your calculator. Now, here's how you could do this with using your exponents. Here's how I would enter this. Parentheses 6 divided by 5, close parentheses, raised to the parentheses 1 divided by 5 power, close parentheses. Or you might have a fractional key on your calculator that will do it. So again, you and your calculator must become 1, and you should get about 0.0371 when you subtract 1 from both sides. So let's go back to that last slide there. Now notice once you take the 5th root or raise it to the 1/5 power, that you've got to subtract 1 here to get R by itself. So making the decimal into a percent, you would end up, you'd need an interest rate of 3.71% in order to obtain the goal in that part of the problem. Now, continuous compounding. The more often interest is compounded within a given time period, the more interest will be earned. Surprisingly, however, there is a limit on the amount of interest, no matter how often it is compounded. You know that with the bankers. They're not going to give you too much here. All right, now it says, suppose that $1 is invested at 100% interest per year, compounded n times per year. Then the interest rate in decimal form, of course, is 1.00, and the interest rate per period is 1 over n. According to the formula with P equals 1, the compound amount at the end of 1 year will look like this formula. A equals 1 plus 1 over n raised to the n power. What do y'all think? Now, using a calculator, we can get the results of the various values of n. Now, notice as n increases, the value of that 1 plus 1 over n to the n power gets closer and closer to some fixed number. And this is indeed the case. This number is the number e. Now, e in mathematics is a real number and not a variable. So as n gets extremely large, and there's a lot of real-life applications for this number e here. I mean, some of you are familiar with the number pi, the transcendental figure that relates the circumference of a circle to its diameter, 3.14159. A lot of people have never heard of the number e that deals with exponents, but e to 9 places is about 2.7182818828, and we can go on forever. This would never end, never repeat, like pi. It just deals with exponents. And it just so happens there's a continuous compounding formula. If P dollars are deposited at the rate of interest R compounded continuously for T years, the compound amount in dollars is given by this formula. Now, I call this the shampoo formula. A equals PE to the RT power, or the PERT formula. Isn't that the shampoo with both shampoo and conditioner in it, PERT? I don't know if any of you ladies out there have used it, or even gentlemen for that matter. But I noticed they have even a Publix PERT and different kind of PERTs in different places. So stop it, young. Get on with the lesson. Now, you use this formula for continuous compounding. So whenever you see these words here, continuous compounding, you're not using that one that says, we were doing it quarterly or semi-annually or annually. You use this formula, PERT, on the test. All right, so it says on example 3, suppose $5,000 is deposited in an account paying 3% interest compounded continuously for 5 years. Find the total amount on the deposit at the end of 5 years. So all we're doing here is we are plugging in 5,000 e to the 0.033% for 5 years. And then when you go to enter this, here's how I would enter this on your calculator. I would go 5,000. Now, to get E, you usually have to hit the second key. And let's see here, the second key, and it depends on the calculators, but usually you are going to hit this ln here, which we'll get to in later lessons. Now, when you hit 5,000 second ln, that's at least what my calculator does here, it will put E to some caret here, all right? And then sometimes it'll even put a parentheses, which in this case, it's a good idea because, again, you have e raised to some power. Now, remember, e is 2.718, all right? And then we'll put times 5 here and close. And then you should get about $5,809.17. So always make sure that, you're checking your calculator, you're using it, you're becoming one, because when you get to that test, you're really going to have to practice a lot and make sure you're getting these in the homework correct. Okay. So check that the daily compounding would have produced a compound amount about 3 cents less than before. All right, in example 7, we found that $1,000 invested at 4% compounded quarterly for 10 years grew to $1,488.86. This was earlier. Compare the same investment compounded annually, semi-annually, monthly, daily, and continuously here. So substituting into the compound interest formula and the formula for continuous compounding gives the following results for the amounts of $1 and $1,000. All right, so for $1, here we got compounded annually, semi-annually, so check the chart out here. Okay, continuously, and $1,000 there. And which one looks the best to y'all here? Compounded annually, $1, semi-annually. It looks like continuously is going to be just a tad better, doesn't it? If you look at the chart there. So that's just plugging in some stuff. So compounding semi-annually rather than annually increases the value of the account after 10 years by $5.71. Quarterly compounding grows to $2.91 more than semi-annual compounding after 10 years. Daily compounding yields only 96 cents more than monthly compounding. I don't know if we're going to get rich on any of these versus the other. Each increase in the frequency of compounding earns less and less additional interest until growing from daily to continuous compounding increases the value by only 3 cents. All right, so make sure you can do the 2 formulas for compounding, both the N one, depending on how many compoundings per year, and the continuous one using PERT. Bob Young signing off.